space telescopes. People who don't believe the moon landings happened asking why these telescopes have been pointed to Earth to show the Apollo 11.
Imagine aiming Earth's most powerful telescopes at the Apollo 11 landing site.
Flight of Apollo 11, beginning 30 hours of continuous coverage of the lunar landing.
And man is about to land on the moon.
Expecting undeniable proof of humanity's greatest achievement. Shockingly, even today's technology cannot clearly reveal many objects left behind. Though the moon sits only 240,000 miles away, atmospheric distortion, resolution limits, and brutal lunar lighting obscure fine details. When scientists pushed these instruments to their limits, the results were unsettling, forcing a re-evaluation of what can truly be observed from Earth and exposing how fragile our sense of cosmic certainty really is. Limits of Earth-based telescopes. When scientists turn Earth's most powerful telescopes toward the Apollo 11 landing site, their expectations run high. After all, this historic spot is only 240,000 miles away, a distance that might seem manageable in cosmic terms. Yet, despite the hope of spotting the lunar module or even astronaut footprints, the details remain stubbornly hidden. The size of objects left behind is simply too small to resolve clearly with even the best Earth-based optics. The lunar module's descent stage, for example, measures roughly 13 feet across without the landing gear, smaller than many might imagine. At the same time, the moon itself appears tiny, spanning just over half a degree of the sky from Earth's perspective. This means telescopes need extraordinary resolving power to distinguish objects only a few feet wide on the lunar surface. But here's the catch. The laws of optics and atmospheric interference set hard limits on what is actually visible. Even the largest telescopes on Earth struggle to break through these limits because viewing from the ground means looking through the thick and turbulent layers of our atmosphere. This distortion blurs images and restricts the finest details telescopes might otherwise reveal. What can be seen instead are vast lunar features like large craters or dark volcanic plains. But when it comes to the Apollo equipment, they shrink to mere dots or disappear completely. Scientists and enthusiasts alike have tried pushing telescopes to their finest limits for decades. The hope was that modern technology and clever imaging techniques could tip the scales in favor of visibility. But reality keeps reminding us that Earth's atmosphere acts as a heavy veil between us and the moon's surface, frustrating even the most advanced optical instruments. One key point is that all 6 Apollo landing sites face Earth due to tidal locking, meaning the same lunar side always looks toward us. That alone should help with visibility, keeping the sites on the front stage for observation. It also means that any potential signals, lights, or surface disturbances are technically pointed right at our best telescopes. Yet, a clear image of the landing areas remains frustratingly out of reach, underscoring a deeper challenge. The inability to see Apollo artifacts directly from Earth has puzzled many and fueled debates, sometimes even unnecessary doubts about the moon landings. But this absence of clear visuals is not about conspiracy. It's about physics and the reality of astronomical observation. Without leaving Earth orbit, our perspective remains fundamentally limited. Despite these constraints, scientists found ways to improve image clarity, using clever methods like stacking hundreds of video frames to balance out atmospheric distortion. Even then, the details are washed out, and what might be richest with historical significance looks small and indistinct at best. This struggle is a powerful reminder of how space exploration, while spectacular, still battles natural limits. All these efforts set the stage for more precise examinations with different approaches and technologies, hinting that the full story lies beyond Earth's surface. The story of Apollo sites and what telescopes reveal is not one of failure, but of the immense challenges we face when peering into space from our fragile blue planet. The real breakthrough came when looking beyond these above-atmosphere limitations, promising to reshape how we understand what can and cannot be seen. The invisible obstacles created by our atmosphere bring us to the next barrier facing lunar observation: atmospheric challenges. Earth's atmosphere is a dynamic, shifting barrier that shapes how we see celestial objects. When we look through a telescope from the ground, we aren't peering directly into space. We're looking through layers of air that ripple and bend light unevenly. These effects cause what astronomers call seeing conditions, which vary night to night and even minute to minute. Even the clearest skies can have pockets of turbulence that blur and distort lunar images. This makes a huge difference when you want to spot something as small and subtle as the Apollo landing site equipment. The light from the moon passes through about 62 miles of life-sustaining but visually disruptive atmosphere before it reaches a telescope lens. Variations in temperature, air density, and wind speed cause constant refraction, bending the light unpredictably. The result? Crisp details become ripples, and sharp edges dissolve into flickering shadows. Astrophotographers have found ingenious solutions to mitigate these effects. A method that has gained much popularity is stacking, which involves merging together hundreds or thousands of separate frames to smooth over the atmospherics. This method can highlight details that are not discernible in single images and mask some of the noise that comes from air movement. However, stacking does not help in overcoming the resolution, which is restricted to the basic distortions of Earth's atmosphere. Adaptive optics technology presents an advanced solution. It is capable of correcting the distortion of the Earth's atmosphere that is affecting telescopic images by real-time measurement and, consequently, mirror modification. This approach furthermore assists some observatories in surpassing even Hubble, the renowned space telescope, in terms of image quality for certain objects. Nevertheless, there exist physical barriers in the case of tiny moon artifacts. Even with this exceptional adjustment, one could rarely expect to see good pictures. Moreover, a few big observatories are resorting to the method of interferometry, which merges several telescopes into one extremely large aperture. The combined size is over 200 feet. The technique is able to enhance the resolution to show details of the moon that are 430 feet wide. However, the lunar module or rover, the size of which is approximately 1 pixel, still remains indistinguishable due to being smaller than a single pixel. The atmosphere, in addition, brings to bear temporal limits. For the most distinct visuals, the moon should be high in the sky, at the time of the atmospheric path being the shortest, and things like jet streams or quick air motion should be practically non-existent. It is a matter of being patient and meticulous with timing to get these perfect moments, which is a challenge that both amateurs and experts have to face. These difficulties show how unkind the view from Earth to the moon's surface is, even with the most advanced technology. It is a struggle between light and air, where even the tiniest flaws are blown up, which in turn hinders the aim of direct viewing. One cannot be surprised that the Apollo landing sites are so hard to spot through Earth-based telescopes. As we consider these atmospheric puzzles, it's remarkable that dedicated amateur astronomers still manage to capture incredible lunar detail with the right tools and techniques. Amateur astronomers' best views. Amateur astronomers have pushed telescopes to impressive limits in their quest to glimpse Apollo landing sites. Using hobbyist setups, some have succeeded in capturing images that reveal craters as small as 1 mile across. An extraordinary feat, given the challenges posed by atmospheric distortion. These images focus on areas like the Sea of Tranquility, home to Apollo 11's historic touchdown. offering a glimpse into the lunar surface rarely seen from backyards. One remarkable achievement is the identification of craters named after Apollo astronauts Neil Armstrong, Buzz Aldrin, and Michael Collins. Their proximity to the landing site adds emotional resonance, linking human history to observable lunar geography. Just a few miles away lies the Cat's Paw Crater Group, a recognizable cluster that helps amateurs orient their views. Despite these successes, the actual Apollo 11 landing site occupies less than a single pixel in these images, making it impossible to discern any objects left behind. Accomplishing this requires a combination of excellent equipment, ideal atmospheric conditions, and thousands of images taken over multiple nights. Stack processing becomes essential, where software filters out the worst frames caused by atmospheric turbulence, then sharpens the remaining data to produce the clearest possible view. This painstaking effort exemplifies the dedication and skill within the amateur astronomy community. Even so, the images pale in detail compared to the kinds of views offered by professional observatories, and certainly nothing like orbital photography. To put it in perspective, a similarly sized area on Earth blurred to this degree might show a large copper mine, a massive feature visible only because of its incredible size. Smaller human-made objects vanish into the haze, just as the lunar modules do on the Moon. Despite these limits, amateurs gain valuable experience learning how to observe the terminator, the line between moonlight and darkness, which enhances contrast and reveals subtle surface textures. Targeting observation around lunar sunrise or sunset maximizes shadows, making topography stand out. This careful timing is crucial for spotting smaller features on the lunar surface. Amateur astronomers also focus on observing the Moon when it is near its zenith, directly overhead. This position reduces the thickness of the atmosphere the light must travel through, lessening blurriness. By analyzing seeing conditions with advanced weather and atmospheric models, hobbyists improve their chances of capturing clear images. Although direct views of Apollo hardware remain beyond reach for most, these efforts still bring the Moon closer and deepen our appreciation for what lies on its surface. The passion and ingenuity of the amateur community keep the spirit of lunar exploration alive, even from earthbound perches. Yet, as impressive as these glimpses are, they highlight the limits imposed by our planet's atmosphere and signal the need for even more advanced technologies. Modern observatory breakthroughs. Professional observatories have taken lunar observation to levels far beyond what hobbyists can achieve, thanks to advancements in technology that push the limits of ground-based astronomy. One of the most significant developments is adaptive optics, which compensates for atmospheric distortion in real time. By rapidly adjusting telescope mirrors to counteract the turbulence of Earth's atmosphere, adaptive optics sharpens images dramatically. This technology has elevated observatories to outperform some space-based telescopes, which is remarkable considering they're still looking through our thick, ever-changing air. However, even with adaptive optics, these observatories face fundamental limits. Their ability to resolve details hinges on the size of the collecting mirror and how effectively it corrects for atmospheric effects. Interferometry takes this a step further by linking multiple telescopes spread over hundreds of feet to simulate a single, much larger instrument. This technique boosts angular resolution significantly, allowing observatories to detect lunar surface features as small as approximately 430 feet across. Despite these impressive capabilities, the lunar module, which measures barely 13 feet across, is still far too small to be resolved as an individual object. What professional observatories can detect are broad lunar features, such as the edges of craters or variations in surface brightness caused by different materials. They can almost tease out the shadows and shapes around the Apollo landing regions, but still come up short of revealing the actual hardware left behind. Simulated images from facilities like the Very Large Telescope in Chile illustrate just how close we can come. These views show lunar landscape details far sharper than what a backyard telescope or even the Hubble Space Telescope can achieve from Earth orbit. But even at this pinnacle of ground-based astronomy, Tranquility Base, the site of Apollo 11's landing, remains indistinct.
Can we see any of these lunar campsites from Earth today? The Apollo 11 site is far too small to see from Earth. Even the most powerful telescopes can't pick it out.
No telescopes on or above Earth possess the resolution necessary to produce a clear, direct image of the lunar modules or rover vehicles. The reason lies partly in physics again. Angular resolution depends heavily on the telescope's aperture size. To see an object as small as the descent stage clearly, a mirror or an array with an effective size of several hundred feet across is required. Building and operating such an instrument on Earth is currently impractical at best. The atmosphere, despite adaptive optics, still blurs the view enough to keep these artifacts hidden. Additionally, professional observatories usually focus on brighter or more scientifically intriguing cosmic targets, often leaving lunar surface studies as a low priority. The equipment may be capable, but telescope time and resources are limited. When lunar observation is conducted, it's mostly for testing atmospheric correction technologies or studying large-scale lunar geology, rather than hunting for human-sized remains. Still, the progress in ground-based observatories has pushed the envelope of what is physically possible through Earth's atmosphere. It highlights our growing ability to peer deeper and with greater clarity into space, while simultaneously underscoring why lunar surface details remain elusive. This paradox between power and limitation is at the heart of why the Apollo sites remain nearly invisible from Earth. Knowing that even Earth's most advanced terrestrial telescopes can't clearly see Apollo equipment sparks curiosity about other tools, like the famous Hubble Space Telescope in orbit. Could a telescope beyond Earth's atmosphere provide the breakthrough we're looking for? Space telescopes' surprising limitations. At first glance, the idea of using a space telescope like Hubble to photograph the Apollo landing sites seems like the perfect solution. Orbiting above Earth's atmosphere, Hubble avoids all the distortion caused by air turbulence, in theory providing crystal-clear views. However, the reality of lunar observation with Hubble is more complicated and surprisingly disappointing. Hubble was never designed with lunar surface photography in mind.
The Hubble Space Telescope was indeed designed to look at very faint objects at astronomical distances. It was just not designed to take high-resolution images of small objects at fairly close ranges like to the Moon.
When Hubble's camera is aimed at the Moon, each pixel covers about 560 feet of lunar surface, enormously larger than the 13-foot descent stage left by Apollo astronauts. The lunar module's size is roughly 1/3 of 1% of a single Hubble pixel's area. This means the module would be lost within 1 pixel, unable to be distinguished from the surrounding landscape. In other words, Hubble's resolution is not fine enough to image such tiny objects distinctly. The consequences are clear. Even though Hubble can image distant galaxies billions of light-years away, it does not have the necessary resolution to capture objects as small as spacecraft left on the Moon's surface. Its design favors deep space, faint objects, rather than the sharp, close-up details required for lunar archaeology. This limitation is one of those fascinating conflicts where a tool's incredible capability in one arena falls short in another. To overcome this, astronomers have theorized that a telescope with a mirror at least 300 feet across would be needed to reliably detect and identify the lunar modules from Earth orbit or lunar orbit. Such an instrument would be 100 times larger than Hubble, an engineering challenge that humankind has not yet conquered. The scale and cost of such a telescope put it squarely in the realm of future, not present-day projects. Interestingly, some Earth-based observatories despite looking through the atmosphere, have technically outperformed Hubble by combining adaptive optics and interferometry. Their effective aperture sizes rival such enormous scales. But as mentioned, even these giants cannot distinctly reveal Apollo hardware, proving just how minuscule those artifacts are compared to the vastness of the lunar surface. Satellites orbiting the Moon have taken up the task with much greater success. They operate much closer and use specialized cameras with extremely high resolution, reaching down to fractions of a foot per pixel. These orbital imagers reveal unmistakable details of the landing sites, from footprints in the regolith to the hardware itself, creating a sort of celestial time capsule. Yet, for those of us on Earth hoping to glimpse evidence of Apollo through a telescope, the truth is humbling. Our best visible approach has been limited not by lack of technology alone, but by the immutable laws of optics and distance. The Moon's hidden relics remain just beyond the gaze of our most powerful eyes, a ghostly reminder of the vast gulf between seeing and truly witnessing. The quest to observe Apollo 11 from Earth challenges our understanding of observation itself, but it is a testament to how human ingenuity adapts and reaches, pressing on toward clarity in ways both scientific and poetic. Looking forward, lunar orbiters bring a new dimension to this story. Orbital imaging advantage. The limitations of Earth-based and even space telescopes pushed scientists to rely on an entirely different perspective: lunar orbit. By sending cameras into orbit around the Moon itself, we bypass the distorting effects of Earth's atmosphere and drastically shrink the distance between observer and target. This approach transformed lunar observation, allowing unprecedented detail of the Apollo landing sites to come into focus. The Lunar Reconnaissance Orbiter, launched in 2009, carries narrow-angle cameras capable of capturing images that span about 1.5 miles with an astonishing resolution of half a foot per pixel. At this scale, objects like the lunar module, which is around 13 feet wide, appear approximately 20 pixels across, revealing detailed shapes rather than mere points of light. This technological leap finally allows us to see the equipment left behind, including the rovers and scientific experiments. More than static images, repeated passes at different lighting conditions let scientists create time-lapse animations showing shadows shifting over footprints and equipment. These dynamic views prove that the artifacts of the Apollo missions remain intact, protected in the Moon's harsh, airless environment. It's like unwrapping a historical time capsule frozen in time, preserved for decades beneath an unchanging sky. The images from lunar orbit carry emotional weight beyond their scientific value. They offer undeniable confirmation of humanity's first steps beyond Earth and the Cold War space race victory, all visible from a vantage point closer than any Earth-based observation. This visual confirmation quiets lingering doubts and brings the story of Apollo back into sharp focus for each new generation. Yet the clarity afforded by lunar orbit makes the limitations of other observation methods starker. It is only by traveling that extra 60 miles above the lunar surface, just above our 62-mile-thick atmosphere, that we can escape Earth's obscuring veil.
The world watched as the Saturn V launched Apollo 11 into space, from Cape Kennedy in Florida. Man's journey to the Moon would become the defining moment of the second half of the 20th century.
Without this perspective, much of the Moon's secrets remain hidden in the haze, teasing our curiosity but denying precise detail. These orbital images have also helped map the terrain around the landing sites in incredible detail, informing future missions with exact measurements of slopes, crater locations, and surface conditions. They pave the way for the next chapter of lunar exploration, offering both scientific insight and navigation aid for astronauts who may soon return. Even with this breakthrough, what scientists saw in some orbital photographs brought an unexpected and unsettling realization. The pristine state we hoped to find had begun to change in ways no one anticipated. This gradual transformation revealed itself subtly, almost imperceptibly, but with implications that compelled careful study. The contrast between the untouched appearance from afar and the surface's actual condition emphasizes how delicate the lunar environment is and how even the smallest forces can alter the landscape left by Apollo. The moon, once thought to be static and eternal in its silence, proved to be more dynamic, and the story of what's left there more complex. This troubling discovery ushers in a new chapter of lunar investigation, where questions about preservation, decay, and change redefine our understanding of humanity's legacy on the moon. The unsettling changes detected from orbit set the stage for a deeper look at what Earthbound scientists were beginning to fear. The terrifying discovery. When scientists zoomed in on the Apollo 11 landing site using every tool available, including the extraordinary images gathered from lunar orbit, they encountered something unexpected. The evidence of human presence was fading. Footprints, rover tracks, and even some equipment appeared less distinct, as if slowly disappearing or being altered by unseen forces. This raised alarming questions about how stable the lunar environment truly is. Without an atmosphere to protect it from solar radiation, micrometeorites constantly bombard the lunar surface, gradually erasing fine details over time. Dust moved by electrostatic forces can settle and resettle, subtly shifting footprints and covering objects once thought permanent. What was once considered a frozen, unchanging landscape turned out to be vulnerable to slow but relentless natural processes. Scientists grappled with the reality that what we assume to be a celestial time capsule may be less permanent than imagined. The fading contrast in orbital imagery suggested that parts of Tranquility Base were gradually blending back into the lunar regolith. This loss of detail unnerved many, challenging long-held beliefs about the moon's inert nature, and reminding us that even the vacuum of space is not immune to change. More unsettling still was the knowledge that without direct, regular monitoring, more evidence might vanish entirely, erasing physical proof of one of humanity's greatest achievements. This invisible erosion unfolds on a timescale too slow for casual observation, but steady enough to matter deeply to historians and scientists alike. The revelation sparked discussions about protecting the landing sites from future disturbances, including astronaut visits and robotic missions. Preservation of these historical locations now become a priority, not just for nostalgia, but to maintain a record of the dawn of human space exploration. This gradual fading also sparked fears about what might happen if we lose track of these sites altogether. Could the proof of humanity's giant leap be wiped away, leaving only stories and photographs as evidence? Such a possibility adds a layer of urgency to modern lunar exploration and conservation efforts. Despite these fears, the lunar surface remains a quiet witness to the past, but one that requires careful stewardship. The fragility of these traces underscores how precious our first footprints truly are in the vastness of space. The horrifying reality of a transforming moon pushes scientific curiosity and human responsibility into a complicated future, where observation extends beyond discovery to preservation. Some researchers describe the discovery as a psychological shock rather than a scientific surprise. The moon had long been portrayed as a perfectly preserved archive, yet the slow degradation of Apollo's traces forced scientists to confront how temporary even historic milestones can be. The idea that humanity's first off-world achievement could quietly fade unsettled both engineers and historians. This realization also reframed how future missions are planned. Landing too close, Firing descent engines or even orbiting repeatedly over sensitive regions could accelerate surface changes. What was once seen as harmless observation is now understood as an active influence, adding pressure to rethink how exploration is conducted. In a broader sense, the fading Apollo sites became a warning. If humanity cannot preserve its earliest steps beyond Earth, it raises deeper questions about how we will safeguard future milestones on Mars, asteroids, or distant moons. The moon's quiet erosion stands as a reminder that progress, without care, can erase its own legacy. Observing these subtle but profound changes reveals not only the challenges of deep space archaeology, but also the enduring mystery of our place in the cosmos. The future of lunar observation. As we stand on the edge of a new era in space exploration, the quest to observe and understand the Apollo landing sites continues to evolve. Future lunar missions promise to bring us closer than ever before, with plans to land new astronauts near historic sites and deploy advanced robotic explorers. These missions will offer fresh opportunities to study, preserve, and even restore humanity's first footprints on the moon. Improved imaging technology is at the heart of this future promise. Next-generation lunar orbiters and landers will carry cameras capable of capturing even finer details, perhaps down to the sub-inch scale. Coupled with innovations in artificial intelligence and data processing, these instruments could detect subtle changes in the lunar environment, revealing how the surface evolves over time under solar winds and micrometeorite impacts.
They would continue to do experiments on the moon, testing the solar wind and laying out equipment that would send results back to Earth.
Beyond detailed imaging, the rise of international collaboration aims to ensure that lunar exploration remains a collective human endeavor. Agencies from around the world are planning ambitious missions that include scientific research, resource utilization, and heritage preservation. This cooperative approach enhances the likelihood that Apollo's legacy will be respected and integrated into the moon's future. There is also growing interest in protecting the Apollo sites as cultural and historical landmarks, similar to UNESCO World Heritage Sites on Earth. Efforts are underway to establish guidelines that minimize disturbance from future landings and rover explorations. This conservative mindset marks a shift, recognizing that while the moon is a frontier for discovery, it also holds irreplaceable human history. Technological advances in Earth-based and space telescopes continue as well. Concepts for massive space telescopes with mirrors hundreds of feet wide, deployed in lunar orbit or at Earth-Moon Lagrange points, could one day attain the resolution required to image Apollo hardware directly. Although such projects are decades away, they represent the ambition and ingenuity that fuel space science. Amateur astronomers and citizen scientists also play a critical role in the future of lunar observation. With increasingly affordable, high-resolution cameras and sophisticated software, dedicated hobbyists contribute valuable monitoring and data analysis. Their passion and perseverance keep the spirit of lunar exploration alive and democratize the quest to glimpse our celestial neighbor in ever greater detail. Moreover, the moon itself may become a platform for astronomical observatories free from Earth's atmospheric disturbance. Telescopes built on the lunar surface or in orbit could peer deeper into space and also scan the moon's surface with unprecedented clarity. This dual-purpose use of the moon could tie together observations of Earth's closest neighbor with explorations of the farthest reaches of the cosmos. As humanity prepares to return to the moon, the mystery and allure of Apollo's remnants inspire not only scientific inquiry, but also a profound reflection on our place in the universe. The challenges and surprises uncovered so far remind us that space is as much a realm of change and uncertainty as it is of wonder. The search to observe, protect, and understand the Apollo legacy is a journey that intertwines technology, history, and human curiosity. Each new image, each advance in observation, brings us closer to the moon's secrets while deepening our connection to humanity's first steps beyond Earth. Public engagement and education are also shaping the future of lunar observation. Virtual reality reconstructions, interactive maps, and open-access mission data allow people worldwide to explore the moon digitally, fostering a deeper appreciation for lunar history without physically disturbing sensitive sites. These tools help bridge the gap between exploration and preservation. Legal and ethical frameworks are beginning to emerge as well. Space law experts are debating how existing treaties apply to heritage protection beyond Earth, raising questions about ownership, responsibility, and stewardship. How humanity answers these questions may define how future generations interact with off-world environments. Ultimately, the continued study of Apollo's legacy is about more than artifacts on lunar soil. It reflects humanity's desire to remember its milestones, learn from past exploration, and approach the cosmos with humility. The moon stands as both a scientific laboratory and a mirror, reflecting who we are and who we aspire to become. We've explored why even the most powerful telescopes can't fully reveal Apollo 11's landing site, and how lunar orbiters provide stunning glimpses of our historic legacy. The moon holds many mysteries, and as technology advances, we'll keep uncovering its secrets. If you've enjoyed this journey into lunar observation, please like and subscribe for more fascinating space stories.